After receiving his doctorate at the University of Ulm, Ralf Metzler went to Tel Aviv University for a postdoc with Professor Yossi Kafler. He then continued for a second postdoc with Professor Maren Kardar at MIT before his first faculty appointment as an assistant professor at the Nordic Institute for Theoretical Physics in Copenhagen. Ralf then became associate professor at Canada Research Chair for Biological Physics at the University of Ottawa. In 2007, Ralf was appointed as a professor at the Technical University of Munich, and since 2011, he holds the chair for theoretical physics at the University of Potsdam. In 2012, Ralf was also a Finland Distinguished Professor at Tampere University of Technology. Among others, Ralf was awarded the 2017 Sigma Phi Prize and Alexander von Hilbert Polish Honorary Research Scholarship. Ralph's work focuses on statistical and biological physics, in particular on stochastic processes and their applications. We are very happy to have you. You may please begin your talk.
Thank you for this very generous introduction. It's a pity that this is an online talk. I would love to be in Trieste and enjoy the landscape and the food, but next time. So I want to talk about fractional from a different perspective today, not from a fractional derivative or something perspective, but from the perspective of fractional Brownian motion, where you have long-range correlations in your noise. And there's also some interesting effects there. For those who didn't hear, the cover slide is not very colorful, but this is Trieste in the eyes of William Turner, the famous painter who painted the Bay of Trieste. I don't know when this was, more than 100 years ago for sure. So if you're interested, search for William Turner. What we do in my group is we're interested in stochastic processes. We come up with models, but typically motivated by measured data or other kind of input information we get. And then we try to come up with these models, analyze their behavior. And of course, the whole thing starts with Brownian motion that was described by Einstein and Smoluchowski. And it's characterized by a mean square displacement, the second moment, that scales linearly with time. And then, you know, we have this beautiful Gaussian probability density function that both are characteristic of Brownian motion. In many systems, though, this linear time dependence of the mean square displacement is changed to a power law time dependence, where alpha is the anomalous diffusion exponent. And later on, I will also introduce the Hurst exponent, which has a longer history, actually, and is just defined by alpha over 2. I'll mention it again afterwards. And then when you have these data, I mean, one of the things you first ask, is it actually a Gaussian process? And for that, for instance, you might want to look at the kurtosis. This is a fourth order moment that you get in here. And depending on the value of the kurtosis, you can judge whether it's Gaussian or not Gaussian, what you say. And another question that I will not pay too much attention on today is whether the time series that you look at are ergodic or not. And ergodicity I typically define in the very simple Boltzmann-Birkhoff-Khinchin sense that time averages, long time averages converge to an ensemble average if the system is ergodic, and there might be discrepancies. In non-ergodic systems, they are not the same, obviously. And one can then also quantify the fluctuations from a single time average, from a single trajectory to the next by, for instance, here, this higher order moment, the ergodicity breaking parameter. If you're interested in that, you can check here this review article. And of course, also there's systems that are non-stationary when a time average depends on how long your time series is. Just an example for what can be measured. This is from Yuval Garini's lab at the Technion. And you can see here these little trajectories, these colorful trajectories. These are simultaneously measured the endpoints of the chromosomes in a living cell. So this can be resolved on a few nanometer resolution. And of course, this delivers all kinds of information on how the chromatin is actually arranged and functions physically. Here, these are very colorful trajectories from Diego Krupp's lab. These are little potassium channels moving in a membrane of a living cell. And all these kinds of experiments or simulations, they provide us with time series, stochastic time series, and we want to analyze them and find out more about the system. Now, another topic that has been very popular the last couple of years is actually non-Gaussianity. So there are many systems that are called Fickian yet non-Gaussian. And there's a history, for instance, in glass forming materials in simulations by Walter Kob. And Steve Grunick actually has a whole factory of beautiful experiments showing Fickian but non-Gaussian diffusion. By the word Fickian, I should have said, I mean exactly this linear time dependence of the mean square displacement. It's a term that's more used in chemistry or geophysics. So look at this system here. This was experimentally studied by Yael Reuchmann at Tel Aviv University. And she has little obstacles. These are little pillars, these circles with a dark fringe. So they're you look from the top and they stand on a surface, and then you have these fluorescently labeled traces. They have to move in between those obstacles. And what they see is that in all the cases, the mean square displacement is linear in time. It has a distribution of the apparent diffusion coefficient from one trajectory to the next. And it has a variation of the anomalous diffusion exponent, although it's always centered around 1. So the ensemble average is linear, but now look at the displacement distribution. You see that there are cases, this is log versus lin, you see there are cases where the tails are perfectly linear. So these are non-Gaussian distributions. In fact, these are Laplace distributions. In this case here, you see the other cases that are plotted here, they have this Gaussian shape on the tails, but even though they look Gaussian here, if you look closer to the center, you see a little cusp. And that's also an effect in disordered environments. So this has been very popular, this topic, and I want to start with this and then come over to anomalous diffusion. Now, let me introduce one system to you that's maybe the simplest one, in which we have a stochastic diffusion coefficient. So this is a very simple protein, very small protein. These are simulations by the group of Eiji Yamamoto in Tokyo. And the typical thing for these proteins is that they have a relatively shallow energy landscape, and they have relatively small minima in which, of course, the protein can assume certain configurations. And actually, oops, what did I do here? It has some configurations that are very compact, in which, of course, the hydrodynamic radius is very small. And then it can assume other kind of configurations, as you see here, and actually become extremely elongated. And we quantified this by measuring the gyration radius of the protein as function of time. And this is this plot here. So the gyration radius is here. Look at the gray curve, and you see that sometimes the protein is more elongated, sometimes it's very elongated. And to the bottom, we plot the time local diffusion coefficient. And you see when it's elongated, it's slower. The mobility becomes slower. So this is really a one-to-one map. And it shows you that we have a natural example here where the protein, the molecule we observe, has a stochastically varying diffusion coefficient. That's important for the model I want to introduce. Next slide. Another viewpoint of a particle moving in a complex landscape is from a beautiful paper by Denis Grebenko from a few years ago. Somewhere here, I think here, there's the tracer particle. I have some problems with my color vision. This is why. And it's supposed to go to this target. and this is just an artificial image, but the idea is it's moving in something like an actin mesh, as you would have in a cell. There's all kinds of cytoskeletal elements, and now this mesh can breathe. So at one point it is more dilute, and when the particle goes into this dilute part, it's easier for it to move, and then it can possibly move into a more dense area where it becomes slowed down. But if this breathing is fast enough and we follow the particle, again, it will be effectively a time-dependent diffusion coefficient. That would be the annealed limit, and we can view the particle with a stochastic diffusivity. How can we put this in a model? This was first done by my old Ottawa colleague, Gary Slater, who also introduced the term diffusing diffusivity. So the diffusivity is really moving stochastically. The disadvantage of their model was one couldn't solve it analytically. And then, of course, with my friends Igor Sokolov and Alexei Chechkin, they want traditional, Eastern scientists. They want exact solutions. So we found a way to rephrase this model as follows. We look at a particle at position X. We can also phrase it in different dimensions. This is not, I just wrote it in one dimension here. So we have a stochastic overdamped equation here for the position of the particle. It's driven by white Gaussian noise psi, but now the strength of the noise is varying as a function of time. We want it to be a stationary process, and we mainly want the diffusivity to be positive. So this is why we map it on the square of this variable y, and y fulfills this Ornstein-Uhlenbeck process. So you have a fixed time scale here in the confinement, the linear force of the Ornstein-Uhlenbeck process, and eta is an independent white Gaussian noise. So we have two white Gaussian noises in the system. This here determines how the auxiliary variable is developing, and this in turn gives me the dynamic of the diffusion coefficient. Now, the only thing I have to specify on top is what is the initial condition for this variable y, and what I show you now is for an equilibrium initial condition. And once it's equilibrium initial condition, although each trajectory you simulate starts with one value, one fixed value of the diffusivity, in the ensemble, you see that it's developing perfectly linearly. If we divide by time, it's just horizontal, so nothing happens as function of time. Whereas when we look at the displacement distribution, at short times, you see that there are these linear tails in the log-lin plot. So these are exponential tails. And then at long times, you see that the exponential slowly crosses over to a Gaussian. And the crossover can be measured when we look at the kurtoses that are introduced before the fourth-order centered moments. And it starts here, this is for one dimension, it starts with a value of 9, which is the Laplace distribution, e to the minus x absolute. And then here it crosses over to a Gaussian whose value of the kurtosis is 3. And the crossover happens exactly at t equals 1, which is the chosen value in the simulations for the time scale of the Ornstein-Uhlenbeck process. Of course, if you don't start with an initial equilibrium conditions, you get crossovers here. This was studied in this paper also for more complicated versions of this diffusing diffusivity process. Now, so this was kind of preliminaries. Now I want to show you one study that we had a few years ago with Ohad Wilk and my old friend Miki Asaf from Jerusalem. And we looked at all kinds of experiments from friends that we could get hold of. And we used some exponents defined by Mandelbrot to kind of sort the motion. Now, one of the things is we can measure the Hurst exponent or the anomalous diffusion exponent, and when h is different from 1/2, it's anomalous diffusion. It's pretty anomalous, as you see here. And then we have different exponents This is the Joseph exponent, the first one, and this is measuring correlations, long-range correlations in the time series. When it's 1/2, like the first point here, no correlations, but when it differs from 1/2 significantly, you have correlations, positive or negative. We'll come to that. And I colored in blue all those cases when we do have correlations, when the system is governed by such correlations. And you see we start with single atoms, we have traces in cells, we have amoeba, we have ants, and then we have all kinds of larger birds, like kites all the way to storks and vultures. So hopefully the blue here should convince you that there's a lot of processes where we have these correlations. And this I want to study in the following. And what I want to use is a very old process that's going back to Kolmogorov in the 40s and also to Mandelbrot and Van Ness in 68. I want to look at fractional Brownian motion in which the noise is not coupled to the friction by a fluctuation dissipation relation, but we're looking at open systems in the sense of Klimontovich, and this is perfect for biological cells that are far off equilibrium, for animals, for weather dynamics, for finance, and so on. So I want to look at this process. So this is again a Langevin equation, a stochastic equation, where here the generalized diffusion exponent coefficient is a constant. But here now we have a Gaussian noise that is long-range correlated. I define it in a second. The Hurst exponent is allowed to vary between 0 and 1. And this process then gives you anomalous diffusion, where here we have this alpha or 2 times the Hurst exponent. And you see when h is smaller than 1/2, it's subdiffusive. When h is larger than 1/2, it's superdiffusive. Now, the noise is fractional, but the correlations can be expressed like this. This is a version that was introduced by Mandelbrot and Van Ness that they called smoothening. And so you have this little offset delta in here. But if you go to tau that are considerably larger than your delta, you actually get to these power law correlations. So you see that the 2-time correlator goes like this time difference to some exponent. And now you have a prefactor 2h minus 1. So when h is 1/2, it's 0 immediately. That's what we know from Brownian motion. There's no correlations. But when h is smaller than 1/2, you have a negative coefficient. And this is what are called anti-correlations. I'll get back to that. I hope I remember later. So now the fluctuations in the time series are more violent than for Brownian motion. On the other hand, when it's positive, when h is larger than 1/2, it's kind of positively correlated and causes superdiffusion. This can also be seen in this displacement correlator that is defined here. And when I normalize it to the 0 value, it takes on a pretty simple form. And I plot it over here. So for h equals 1/2, that's the center line. You see that the correlations drop off in the bin time immediately to 0 and stay at 0. For anti-correlations, when h is smaller than 1/2, you see that we get these correlations. They cross over the 0 line, they become negative, and then they relax in power law fashion. And this negativity of the correlations, this is what causes the subdiffusion of the trajectory. By the way, for fractional Brownian motion, the area under this correlator for subdiffusion gives you an area of exactly 0. For positive correlations, on the other hand, you have shapes like this. Good. One example where you see both is an older experiment we did with an old friend, Christine Selhuber, who's now in Heidelberg. And she measured very complicated amoeba cells that contain vesicles and all kinds of other particles. But when you look at them from the top and they're nice, happily alive, there's a lot of motion going on in them. And this is caused by molecular motors that are driving the inside of the cell. And when you measure the mean square displacement, you get alpha values that are very high. I mean, this is between 3.5 and 2. This is almost ballistic motion. And then as good with good biology collaborators, you pour all kinds of poisons into the cells. And if you put one poison that's called blebistatin, you see a lot happens. All of a sudden, alpha is very, very small. So here, this knocks out the motors. There's no motion anymore. It's just, you know, things are jittering around a little bit and are very subdiffusive. So once you put the poison, your displacement correlator looks like that. So here the data are superimposed without fit parameter by what we get from the expression for fractional Brownian motion. And you see we have this very sharp crossover to negative values, and then slowly, it's decaying to zero. This system, these cells are naughty. You leave them with the poison, and after some time, they flush out the poison and they recover the motion. The motors start moving again. So after a few half hours, or I don't remember, 1 hour, you see how the positive correlations are building up again. Okay, so this is really particular for this kind of system. So you see the positive correlations that I was talking about, and once you put the poison, we have the negative correlations. Good. Another system, let me be quick here. These are simulated membranes. You view them from the top. So here, these are lipid molecules, the small molecules that make up the kind of liquid of the membrane. And here we have one big protein embedded in the membrane. And then we look at a crowded system where we have lots of these proteins. For the dilute system, when we plot the displacement distribution in a very particular way. It's the log of 1 minus the cumulative probability as a function of the log of R squared. So this really picks out, if we fit the what we see with such a stretched Gaussian, it picks out the power law scaling of the radius that we have in the exponential. So for a Gaussian, this is just an R square scaling. And in the dilute case, we get clear deviations from this square scaling, but it's not linear. It's not the Laplace distribution I showed you before. It's something in between. And we have a simulation, so we can look at the details of the system. What you see here for the dilute case, you see all the lipids when you individually trace them, look at their time average mean square displacement, they all have the same amplitude. Of course, here when your lag time gets close to the measurement time, you get deviations. But here before, you see beautiful, they're all on top of each other. Whereas in the crowded case, you have lots of variation in the amplitude here. So what happens when we have a dilute case? You see when we look at the time local diffusivity from individual trajectories, they look more or less stationary. They fluctuate, but is pretty much around one common value. In the crowded case, we have many examples where we have this intermittent behavior. We have a high diffusivity, then a low diffusivity, and so on. And this comes, of course, from the fact that once you have agglomerations like this, the lipids that are trapped in there, they don't have the same mobility, of course, as the ones that are outside. And once those proteins move a little bit, we can also release those guys trapped in here again, and then others are trapped, and so on. So this is one example, again, where we have a stochastic diffusivity that affects non-Gaussian diffusion. Can we model this in a way? And now now I come to a point where I have to admit that none of us really understand this fractional Brownian motion correctly, fully. Each time we look at something new, we find something new. For instance, here it turns out that if you use this Langevin equation formulation, it gives you somewhat different results from another formulation that I will use later on. We're investigating this at the moment. It's continuing. I don't have a definitive answer, but is interesting. Anyway, so now we go back to our Langevin equation, but now I use this diffusing diffusivity. So the only difference to what I showed you before is that now the whole model is driven by this long-range correlated noise, this fractional Gaussian noise. Here, the Ornstein-Uhlenbeck process is the same as before. Okay. What I forgot to say for the case when this is white Gaussian noise, what we looked at before, is a very robust process. We phrase it differently. We replace the Ornstein-Uhlenbeck by something else, but the phenomenology is the very same. Here it turns out, once we have these long-range correlations, once we have very pronounced memory, it's not so easy anymore. So we looked at it for 3 different realizations. I only show you one here. This is what we call the Prosecco model. Now, all you Italians, you will already know this. This is when my friend Alexei was working with Flavio Serno in Padua, and they were talking about, you know, what will they drink in the evening to celebrate the day's work. And of course, you start with a Prosecco. That's the easy start. And they had in mind that they go to Wien or that they go to Grappa, but they never arrived there. We're still working on it. So in the simplest case that I outlined here, you see that we have 2 different scaling regimes, and this crosses over exactly at this time that we have in the Ornstein-Uhlenbeck process. Here I chose one to start with. And when it's subdiffusive, by definition, by the H, but once you introduce the fluctuations in the diffusivity, it actually crosses over to linear diffusion. What happens is that these fluctuating diffusivities, they destroy the property that the area under the correlator is vanishing. Superdiffusion is not affected by this. Superdiffusion stays superdiffusive, just with a different prefactor. And there's all kinds of strange effects when you look at the effective diffusivity as function of H. You have discontinuities, but the only thing that's the same in all these models is that at short times, you really have these exponential tails. At long times, you have the crossover to a Gaussian. So this is, you can see one can use these models for phenomenology, but the fact that different versions of the model give you very different behaviors. In some cases, subdiffusion stays subdiffusive, or you have continuous behavior of the effective diffusivity, but it's not maybe the most desirable physical model when details matter. So we are continuing to look at these things and so on. How am I in time? Ooh, too much. So a few strange effects of this fractional Brownian motion. Now we look at fixed alpha or fixed Hurst exponent, but we squeeze it inside a box. And inside the box, we know what happens for Brownian motion. That's the center here. So you see it's fluctuating around. It's just bouncing off the walls. And this is the probability density as function of time. We start with an initial Gaussian, and then after some time, it has the equilibrium distribution. That's just an equidistribution along your box. When we have subdiffusion, what happens is when we approach the boundary, you see it really doesn't like the boundary. It shies off the boundary. It moves back into the bulk very quickly. Now, we looked at different implementations of the reflecting boundary conditions. I'll say something on top afterwards, but we use different definitions, and it might change a little bit very close to the boundary, but the main effects remain the same. When the particle goes to the boundary, anticorrelation means that the next step after moving towards the boundary will be away from the boundary. So even though it overshoots a bit, it might be reflected back, but it will continue moving away from the boundary. And that's what you see here. The stationary distribution actually has this inverse U shape. So it's not the equidistribution, it's this shape. And for superdiffusion, it always tries to go in the same direction. And you see it glues on the boundaries. That's also what people know working on active particles. They also like to stick to the boundaries. So that's something we have here. And we get this U-shaped behavior here. Now, as I just said, you might say it's a badly implemented reflecting boundary condition, but what I show you here we use a steep potential, not a harmonic potential, but an x to the 4 potential, and for super diffusion, and you see again that it forms this U-shaped behavior. So this is a phenomenon that we observe in many settings, and together with a colleague, Schemantis Janushonis from Santa Barbara, we apply this as a very, phenomenological model to look at how the density of certain brain fibers is evolving with time. So these are these are maps of these fibers. This is a simulation with super diffusive fractional Brownian motion. Why do we choose it as a model? First, it's an easy generalization of polymer models. We have Gaussian chains. These are still Gaussian, but they have correlations. And then when we look at the time evolution, it shows equidistribution for normal diffusion. So we just use some shapes. This is, by the way, this is a cross-section of a mouse brain with some smoothing algorithm. And here, of course, it can't be reproduced by a Gaussian chain. If we use subdiffusive models, you see that we get a depletion around the boundary. So that's also not showing us the behavior we want. We need to go to super diffusion, and we see exactly the higher density around the hard boundaries. So this is really work in progress, and Schemantas has a very wide view of the applicability of this stuff. This is from a three-dimensional reconstruction. So we slowly move from the backside of the brain forward. You see that there's all kinds of details emerging, and the simulations are actually very nicely agreeing with the measurements of these densities. So one day, maybe the dream is that we can use only simulations to get certain details, and we don't need experiments on mice and other animals anymore. Good. That was a little aside. I have a few more things to address. One is knocking at the door. One is measurements that we look at together with my colleague Carsten Bethe in Potsdam. He's interested in the motion of amoeba cells. They're called dictyostelia. And so we looked at individual cells moving, but in this experiment, they actually created a whole carpet of these cells. So it's on the surface, you have these mobile cells on the surface, and on top of these cells, you put these colloidal particles. So these colloidal particles typically cover several of these cells, and then you see motion of these particles as shown here. And of course, there's anomalous diffusion involved in there, but the most important point is that, again, we see very pronounced non-Gaussianity of the displacement distribution. And it starts with a stretched Gaussian, where the stretching exponent delta is smaller than 1 even. But then as time progresses until the maximum time of the measurement, it actually seems to converge to a Laplace PDF, not a Gaussian. So this Laplace shape seems to be very, very typical for these systems. That's the same thing also for individual cells. Now, for cells, we can understand they have different speeds, they have different persistence, but the fact that it really converges to this Laplace distribution is quite interesting, and maybe it's showing us the strength of the Laplace central limit theorem, that in systems with finite numbers of steps, the tails are normally actually exponential and not Gaussian, which is the limit for many steps. You also see here in the displacement autocorrelation, in the shorter times, we have positivity of the autocorrelation. So this is where we have super diffusion in the mean square displacement. You see there's super diffusion here, and then it relaxes over to normal Fickian diffusion. And one can argue maybe whether one can use versions of fractional Laplace motion that was introduced by Mark Meerschert several years ago to model this, but then we don't use infinite range of the power law correlations, but we can use a finite range correlation. So for some time, it's anomalous diffusion and non-Gaussian, and then it crosses over to normal diffusion, but still stays non-Gaussian. So this is something we're looking at the moment. Now, I'll use a few more minutes on the cases when the Hurst exponent becomes time-dependent and when it becomes space-dependent. So time-dependent, my best example is here when we look again at these membranes. That's now a side view of a membrane from very old simulations we did in Finland. And we showed in this paper here that when we change the temperature at which we look at the membrane, also the anomalous diffusion exponent is changing. So just by varying temperature, we can adjust the diffusivity here. We can go from very subdiffusive to normal diffusive. And there's also other systems where age can vary with time. Now, we asked our mathematician friends in Wrocław, Agnes, Michał, Chris, and Jakub, and they showed us, oh yes, this is well known. Go to modeling of financial data. There is multi-fractional Brownian motion, which is very exciting, beautiful. It took me some time to understand what it means because they use the harmonic representation of fractional Brownian motion. If you rewrite it in this way that I mentioned before, that Mandelbrot actually suggested, Mandelbrot here has a minus infinity in this integral. This is a different version going back to Paul Lévy, but disregard the lower limit here. You have the correlations in here, and here you have the increments of the Wiener process. So for a constant alpha, this is giving you beautiful fractional Brownian motion, not immediately equilibrated, but after a short time it equilibrates, or you can use the, as I said, the minus infinity. But now what the mathematicians like Ayash and Lévy-Vihel are doing, they use an alpha of t, but also inside the integral, it's an alpha of t. It doesn't vary with the internal timescale s of the integral. So when you calculate the mean square displacement, it always looks like t to the alpha of t. I'll show you some plots afterwards. So you may ask, where is the memory? Assume that I have a very low value of alpha in the first part of my trajectory, and then I go to a different value. This should give me a different mean square displacement from the case when it's very high at the very beginning. I can show you differently when you have a Brownian motion and we have a time-dependent diffusion coefficient. And it changes from value 1 to value 2. And then I go to the mathematics and I look at how I describe this. Of course, now my noise strength is becoming a function of time. And of course, it has to be S because it's really varying over time. And when I integrate this, I have these two values, then this is my mean square displacement. It's until I switch it, until I change to a different diffusivity, this should be index 1 here, of course, I get this value. Once I go beyond, I have this value. This is the mean square displacement until I switch, and then this is the growth after I switch. Of course, I have a tau dependence and a t minus tau. And the above formulation, if I had k of t here, this would give me the same thing all over. So something is wrong. Of course, for the financial modeling, it doesn't matter because the only thing they're interested in is the local roughness. They only look at the differential of the process. Whereas we want to know something that accumulates over the process. And what we took as what we chose is that instead of alpha of t inside the integral, we have alpha of s. I don't have a direct physical derivation for this. We're working on this. I show you an alternative model afterwards. But this at least gives us a continuation, a memory of what happens before the switching. Here I want to switch the anomalous diffusion exponent from alpha at time tau to alpha 2. And when we calculate the mean square displacement here, we see that the memory is effective. So of course, before the switching, everything is dominated by alpha 1. After the switching, we get this kind of behavior. So we have a mix of alpha 1 and alpha 2. And when alpha 1 is sufficiently large, it might be larger here than the alpha 2. So it might even dominate the time series through this power law memory after the switch. So when you simulate here, it doesn't look as extreme. We took not an abrupt change. We took an exponentially smoothed change between alpha 1 and alpha 2. And you see here for this first definition, the mathematician's definition with alpha of t, we developed this is alpha 1, and then because it doesn't adjust the prefactor, it just switches to a motion as if the whole motion had been with the second alpha value. It jumps up here and has a different behavior here. And the process up here, the memory multifractional, you see it's continuous, and it just switches to a different roughness, to a different alpha. This is also what I meant before. When you have a smaller alpha value, it's much more erratic. So the mean square displacement shows a similar surprise. The first definition, the mathematician's definition, it shows a completely different scaling of the MSD. That's the second exponent. Whereas when we continue the memory, you see that here it's still growing because the alpha 1 was large enough. And it's a very different situation. Of course, we need to find out what is the real physics here, but we know that this can't be the physics of the process because there's no memory that is preserved. With Jakob, we also looked at a different definition. I mean, this is new stuff. We can define what we want. So he wanted to come from the increments. And so in his model, we have the fractional Gaussian noise. And then we change this to a generalized version where we can have different versions of different values of h at different times. So if we look at a two-time correlation here, it could be a combination of two diffusivities and two Hurst exponents. That's what we wrote down here, and then we can analyze the process. But you see that there's one key property. This is the first alpha value. Here we switch to the second alpha value. It's still perfectly continuous. There's no jump in the trajectories here. It just changes the roughness after the switch. Good. Now, what did I thought I would present a full study here by now, but I was a few weeks at hospital recently, so we didn't finish this project yet. This is what happens when the Hurst exponent becomes space dependent. This is what the biologists want to know when these fibers are growing in the brain and then they cross to a different region where there's a different apparent Hurst exponent. What does it do to the trajectories and so on? So we look at a very simple scenario. We look at what happens when we have one range. I can barely see the difference in the colors. So we have a central range with one alpha, and then symmetrically at x absolute larger than 1, we have a second alpha value. And of course, we can switch them around. And now we start the fractional Brownian motion particle at the center. This is normal fractional Brownian motion. It just switches Hurst exponent when it crosses x equals 1. And it looks like this. So you see for the case when alpha is large in the center, it likes to stay in the center. The same for the incremental fractional Brownian motion. This is the last model I showed you. So here there is a continuous memory, but it likes to be in the center. Physically, you would expect where the transport is fast, you're driven away very quickly. So you should actually be more in areas that are slow in the small alpha. And this only fulfilled by this memory multifractional Brownian motion, the one where we have alpha of s in the integral. So you see here, indeed, the particles like to avoid the central fast part. It's the opposite case when we are slow in the central part. Here again, those two, they tend to go away, whereas the memory model has the motion very close to the center. These are the corresponding displacement probabilities. And here you see that the one with the alpha of s in the integral is most different from the other two, but it also shows this very typical behavior we had earlier for the space dependence when it's in the box. This is for the other case, which is slow in the center. And then we also look at the moments. So here, for instance, we look at the second moment, and normal fractional Brownian motion and the incremental one, they behave almost the same, whereas we see a different scaling again for the memory multifraction. So I don't want to go through all the details. I just want to show you how critical the formulation is for these memory processes. So this is stuff we are working on it. Other groups are working on it. It's, I think, one of the really very dynamic fields in stochastic processes at the moment. And one can measure it. I mean, you can follow particles in inhomogeneous environments, and then you want to marry them with stochastic descriptions and in turn get some information out of them. Good. I'm not too bad in time, actually. Well, let me quickly summarize. So we have single particle tracking, supercomputing. They give us huge insight into microscopic dynamics, single particle dynamics of complex systems. When I have these long-range correlations, I see them across many scales. I showed you drug molecules. I showed you flying birds, many other examples that we have. And this is something we can describe by these long-range correlated processes like fractional Brownian motion. I showed you when there's an inhomogeneity in the tracer example, or in the environment, we get these non-Gaussian displacement distributions. I showed you that fractional Brownian motion shows quite peculiar interactions with the boundaries, hard boundaries or very steep potentials. I showed you this generalization of multi-fractional Brownian motion as a minimal approach to time and space-dependent Hurst exponents. We're still lacking the exact physics, the derivation for these processes. And again, as I mentioned before, the two different versions how I phrase fractional Brownian motion, with this memory integral or with this Langevin equation that I feed with long-range correlated noise, they lead to, in some cases, they lead to different phenomenology. Mean square displacement is different, and so on. So this is something we really need to understand, which is the correct formulation for which problem. What I didn't mention, the displacement autocorrelation function for FBM is not unique. I showed you these plots. It has a negative part for subdiffusion. It has a positive part for superdiffusion. But especially this crossing down to negative and then recovering, you have very similar patterns in other systems. For instance, we use molecular dynamic simulations in this paper where there's a drug molecule in a silica channel, and we see exactly this kind of anti-correlated behavior, although it's not fractional Brownian motion. In an older paper with Stasburov and Eli Barkai, we even had a continuous time random walk in a box. And because you get anti-correlations when the particle is bumping back from the boundary, we found almost indistinguishable correlation functions. So you need to know what you're looking at. You need to look at more than just one quantity. And that's also part of what we called the anomalous diffusion challenge together with some friends from Spain. This is about using data methods, Bayesian analysis, and especially deep learning methods to analyze data and find out what is the process behind, what are the parameters behind. Part of of what we learned in this adventure was published in a Nature.com last year. I also have one with my PhD student where we look at some additional evaluation criteria, and we also have this mini review last year. I should also say there is a special issue of JPhysA on this anomalous diffusion challenge, and as we speak, the anomalous diffusion challenge 2 is happening at the moment, and it's mainly about change point analysis. So if you want, you can still take part. That's what I have. And where can I see you guys? I'm lost. Can you talk to me from somewhere? Thank you.
Yes, I can. I can. So probably did you just change it from a gallery view to a screen?
Yes, somehow. Oh, here.
Yeah.
You're back. Yes, you're back.
All right. So this was wonderful. We are open for questions. I kindly request to raise your hands, and I'll call out your name in the order they appear on my screen. I see Lorenzo has a question. Lorenzo, please go ahead.
Yes, thank you, Pavan, for organizing these talks, and also I would like to thank Professor Metzler to give this nice talk. And I would like to ask if there were observation or experiments where the system exhibits a long memory or a covariance long memory, but with a covariance functions which is not expressed by power laws. It means some particles whose covariance is not expressed by power laws, but nevertheless they exhibit like long-range dependence, or also super diffusion and slow diffusion.
The question is what you mean by long range. So you can always find systems, that have anomalous diffusion and non-normal correlations over a finite period of time. For instance, I showed you these simulations of the membranes. Mm-hmm. So what you see there, it's subdiffusion up to a certain time scale, and from that time scale it crosses over to normal diffusion. So you can actually capture the behavior of the data by having a power law correlation that you cut off at one point. You can cut it off with a steeper power law or with an exponential, for instance. And when you do this, don't ask me why. It's magic, but it really is on top of the data, even in the crossover region. This you can have. You can have other kinds of memory functions. For instance, you have a polymer chain, and in this polymer chain, you have a disturbance. It's going up and coming back, right? And so when it comes back, there's a time delay. The more it moves up, the longer it takes to come back, and that also changes the prefactor. So what you get is that you have exponential contributions that build up something like a power law shoulder. So you have a power law with these exponential with these oscillations on top. But of course, it stops at the end of your polymer chain. So when it's finite, you will have another example where you have these ultimately finite correlations. So you can think of many systems where you have these distributions of correlation times. They exist. They can be measured. Yes.
Okay.
Was this an answer? Then.
Yeah. Thank you very much.
Right. Any more questions? I don't see any more raised hands. So if there are any final comments or remarks, go ahead. All right, there seems none. So thank you very much, Professor Metzler, for
Pleasure.
this wonderful talk. It was very nice to have you here.
Thank you for the invitation.
The pleasure is mine.